So we're going to be doing a presentation on combustion reaction. So what is a combustion? Well, a combustion reaction is basically a reaction where a combustible substance rapidly reacts with oxidizers to produce energy, mainly in the form of heat and light. And that energy is what you see as this fire, as you can see in this picture. Now, the most common forms of combustion reactions are with hydrocarbons, which are substances that contain only carbon and hydrogen. Combustion reactions with hydrocarbons can either produce a complete or incomplete combustion reaction. So, a complete combustion reaction is basically a reaction where there's a sufficient amount of oxygen for the substance to react with. Now, the products mainly include water and carbon dioxide, and this is why control over ventilation of a combustion reaction is key during experiments. Now, an incomplete combustion reaction is when there isn't enough oxygen for a complete combustion reaction. Now, the products of an incomplete combustion reaction usually include carbon monoxide, carbon dioxide, and water. Now, the color of the flame can also be a large indicator of whether the reaction is complete or incomplete. For example, a yellow flame can indicate an incomplete combustion since it produces more light rather than heat. And a blue flame produces more heat and less light, which indicates a complete combustion, as complete combustions are more efficient with heat. So how does a combustion reaction work? Well, first, energy that is stored in compounds as well as energy released or absorbed in a chemical reaction is called chemical energy. Now, during a combustion reaction, it requires energy to break the bond of the reactants, which is endothermic. Now, along with the products of carbon dioxide and water, energy in the form of light and heat is also released, which is exothermic, my bad. So in order for the combustion reaction to occur, initial energy is required to break down the reactants, for example, a spark. Once the molecules are broken apart, they become unstable. And once they become unstable, they will create new bonds and at the same time release energy. So the energy being released exceeds the energy that was initially used to break apart the molecules. And that is called net energy. So this chart indicates the levels of combustion. Now the A line represents the initial energy line of the compound itself, while B represents the initial energy required to actually break apart the molecules. C represents the transition stage, where the molecules are in an unstable as they are all broken apart. And D is the energy level of the final product, which, as you can see, it shows that the energy released exceeds the initial energy used to break apart the molecules. Now, according to the law of conservation of energy, energy is not created or destroyed. Instead, it transforms into different forms of energy. For example, energy that is stored in the compounds, which is chemical energy, are transformed to heat and light energy. As well, the mass of the sun is being transformed into light and heat. Basically, behind combustion reaction, energy is just being converted from different forms.
Thank you, Eric. My job was about current combustion research in this world. Current research regarding combustion-related science is focused on efficiently using fossil fuels and minimizing the impact of pollutant emissions from combustion chambers. The research addresses problems like combustion in diesel engines, gas turbines, and rocket propulsions. This is an ad called Advancing Clean Technology, which is basically one of the goals for combustion research, making sure that there's no pollution in anything.
NETL's high-pressure combustion facility is a unique resource within the National Laboratory System. It provides the test capabilities needed to evaluate new combustion concepts for high-pressure, high-temperature hydrogen and natural gas turbines. These concepts will be critical for the next generation of ultra-clean, ultra-efficient power systems. NETL's high-pressure combustion facility serves two key areas: studying fluid flow and combustion variability, and analyzing reaction behavior during high-pressure combustion. To model and study fluid flow and combustion variability, NETL researchers use computational fluid dynamics and the dynamic gas turbine combustion test rig. How gases flow within a combustor has a major effect on the overall combustion performance, as well as how heat transfers to the combustor liners and turbine blades. If not properly addressed, these factors can severely diminish turbine efficiency and lead to premature wear and component failure.
And that's basically the important part of combustion-related science that most of the research centers do. These are the important research centers list that they're just important. Like the first annual conference of Combustion Energy Frontier Research Center in Princeton, New Jersey, the Combustion Research Group in University of California, San Diego, the Combustion Research Lab in Paul Scherrer Institute, Switzerland, NASA's Glenn Research Center in Cleveland, Ohio, United States, the University of Southern California, California's Energy Institute. This is the logo for Paul Scherrer Institute. It's really important because this is one of the main areas in Switzerland and Europe that does scientific research, so that's the significance here. And this is what NASA's been up to. NASA is also following the same methods as other combustion research things, but their main things like rockets, because propulsions. They also have similar projects like other combustion science researchers, but some of them are really important that I think are relevant. Like one of them is high energy propellants that are metallized gel rocket propellants. Not much is known how they will impact the environment, so research is underway to find out all about it. The United States military is also looking for options to use it as their missile programs. There's also another one called hydrogen combustion. Other research centers are actually doing research about it, but NASA seems a bit more important since they're using it as a better source of aviation fuel for their rockets, and because it's cleaner and efficient to use. This is a high gel propellant picture experiment thing. This is NASA is also researching different types of combustions in microgravity to see what the effect will be in microgravity, of course, and see if it's safer to do it because of all the space travel and for better storage things in space. One such effect is known as flame ball. This is a picture of that. The flame on Earth is of course like an ordinary fire, but in microgravity it'll look like a bulb thing, like a ball, so that has the name flame ball, which is pretty cool. And these are the machines that they use to experiment in microgravity. There's another one. And now to Kalp.
Thank you, Arij. So I'm going to be talking to you about the real-world implications of combustion reactions. So combustion reactions happen all around us. We see them in our everyday life, pretty much everywhere we go. But combustion serves us in a variety of purposes, which includes creating heat, light, electricity, and used as a propellant for rockets, aircrafts, and spaceships. So here are a list of some common combustion reactions that you're probably familiar with. So there's smoking, campfires, forest fires, Bunsen burners, water heaters, and explosives. So you're probably familiar with most of these combustions, and you've probably seen them in the past sometime or the other. On the other hand, there are also many uncommon forms of combustion reactions that you don't see every day, such as the combustion that occurs in internal combustion engines, rockets, coal power plants, and fireworks. So you're probably wondering how these work. So let's start off by looking at the combustion that occurs in an internal combustion engine. So these engines are used in just about all cars today and work in 4 major steps. So here's a quick animation to help guide you through this. So it starts off by the intake valve opening and the piston moving down to allow air and gasoline through. Number 2, piston moves back up to compress the fuel and air mixture to make the explosion even more powerful so it releases more energy. Number 3 is when the piston reaches the top and the spark plug ignites the gasoline and the gasoline explodes, causing the piston to go back down. Once the piston hits the bottom, the exhaust valve opens and the exhaust leaves through the tailpipe. Now, let's move into the combustion that's used to propel rockets. So, in order to launch a rocket or move through space, we must use a complex propulsion system to generate thrust. This thrust is generated using Newton's third law, which states that every action has an opposite and equal reaction. So there's 2 kinds of propellants that are used in most rockets today, liquid and solid. Liquid propellants usually use a liquid fuel composed of either liquid oxygen, liquid hydrogen, nitrogen tetroxide, or hydrazine. As you can see from this diagram, liquid fuel is stored in a different container from its oxidizer. On the other hand, solid propellants use solidified forms of the propellants used in liquid propellants, and the fuel and oxidizers are mixed together, which means they just have to be ignited. In the end, the propellants are both ignited to create enough and are used to create enough thrust to propel the object forward. This thrust is created by the gases escaping after the combustion reaction from the combustion chamber and out into the air, which gives the rocket enough force to move. So that's that. Now here I also have a better diagram which shows liquid propellants. So now let's move into how we can use combustion to create electricity for homes and businesses. So in a coal-fired power plant, combustion starts off when coal is transported from external sources to the power plant. The coal is then grinded into smaller pieces and then burned using a combustion reaction to create heat. The heat changes the water into steam, and the steam is then compressed to the tubes and used to spin a turbine to create electricity. The electricity then makes its way to a transformer where the voltage is increased and it's distributed to homes and businesses. Now let's jump into the combustion reactions that make the fireworks you see every day possible. So it starts off when combustion occurs at the fuse. As the fuse makes its way and lights the propellant, the rocket starts to propel upwards, and as the propellant runs out, the burst charge explodes, spewing stars outward and igniting the stars, which are usually grounded metals and used to create colors in fireworks. So this is basically when you see the colors in most fireworks. So yeah, that's my section. Now I'm going to hand it over to Kevin.
Alright, thank you, Kalp. And I will be briefly talking about future possibilities of implementing combustion. First of all, as he talked about before, I will briefly expand on internal combustion engines. For a long time to come, there will be no alternative to the internal combustion engine. Gasoline is lightweight, relatively abundant, and exists in an easy-to-use liquid state at every temperature humans operate: cars, trucks, boats, motorcycles, scooters, and airplanes. Best of all, it's cheap. The ICE is already supported by an incredibly advanced global infrastructure. Pure electronic vehicles might not see more popularity in the future. However, gasoline-electric hybrids better balance the upside and downsides associated with both technologies and will become more affordable and better in the bargain. By 2040, 40 to 50% of new car sales will be hybrids. So what are the benefits of a hybrid car? First of all, it has lower carbon dioxide emissions, use less gasoline, and release less exhaust into the air. That means you save energy and money. Secondly, hybrids are well suited for driving in the city traffic. When the vehicle is stopped, it uses electricity instead of gasoline. When the gasoline engine isn't running, it's exceptionally quiet. You do not need emission tests, and you will need less maintenance and less frequent oil changes. So how do hybrid vehicles work? Gasoline electric hybrid vehicles contain these main parts. First of all, the internal combustion engine, one you will find on most cars, but the engine on a hybrid is smaller and more efficient. The fuel tank, the energy stored for a gasoline engine. And also the electric motor. It can draw energy from the battery to accelerate the car, but can also return energy to the battery. Starts and stops instantly. The battery, the energy source device for the electric motor. And finally, transmission. Most use conventional transmission, some use CVT transmission. And here's a diagram of a hybrid car. You can see the battery, the power split device, electric motor, the generator, and the internal combustion engine. And there are also other ways hybrids can improve fuel economy. First of all, it has the ability to store energy into the battery. Whenever you step on the brake pedal in your car, you are removing energy from the car. The faster a car is going, the more kinetic energy it generates. A hybrid car can capture some kinetic energy when braking and store it in the battery to use it later. Secondly, sometimes it can shut off the engine. They do not need to rely on the gasoline engine all the time because it has an alternate power source, the electric motor and batteries. Also, it uses advanced aerodynamics to reduce drag. When you're driving on the freeway, most of the work your engine does is pushing the car through the air. The force is known as aerodynamic drag. It can use less energy to accelerate the car when the frontal area of the car is reduced. And finally, hybrid cars use lightweight materials, such as carbon fiber and aluminum and magnesium, so they can be used to reduce weight and reduce energy. And that's it.